forms this accretion disk, and that's visible to astronomers, and now we've zoomed in, you can see the jets of energy coming off this neutron star as it sucks gas off of its companion star. And that's something that you can see, these binary systems, and eventually, this can potentially crash, eventually will spin down and maybe crash into its neighbor. But what if that neutron star was orbiting another neutron star? Two things you can't see, and they're orbiting around each other. How on earth could you see that? Now, I will say, just as an aside, we did see this back in, I think, the 1970s, because both of those neutron stars, or they were pulsars, we happen to be able to see the pulsars. But generally, you're not going to be able to see that. So it's this totally invisible system of one dead star orbiting another dead star somewhere out in space. And we want to be able to see when something very, very interesting happens in that system. Now, to tell you about what you are going to see when you look at this neutron star system, I have to introduce gravitational waves, which means I have to tell you about gravity. So we're taking a little tour into gravity, and the thing I want to just get across in 2 slides here is as a theorist, one of the most important ideas to get across is something called relativity. We hear about special relativity, general relativity. There's actually a really simple idea that's called Galilean relativity, as in Galileo. He thought of this 400 years ago, or something like that. And basically his point was, if you were living inside of the hold of a ship, and you couldn't see outside, and the ship was sailing through very, very smooth seas, you could not tell you were moving. And that was a revolutionary idea, because back then, the idea that you were moving and couldn't tell that you were moving was not an obvious thing, right? Like, you're sitting in a carriage, you're going to notice you're moving, you're bouncing all over the place. We have all had that experience, though. You're flying in an airplane, there's no turbulence, you don't look out the window, you feel like you're stationary. And in fact, the point of Galilean relativity is there's no experiment you can do without opening up the window and looking outside to know whether you're moving or not. All laws of physics have to be true if you're moving at a constant rate. That's all Galilean relativity is. All special relativity is well, what he said, but also the speed of light is a law of physics. Just so happens that if you measure the speed of light, no matter how you move, you measure the same answer. It's just Galilean relativity plus that little observation, and that has some pretty weird consequences. We're not going to get into all of those right now because that's a whole other thing, right? But that means that distances and times all get mixed up. Okay, now what does that have to do about gravity? So I'm going to ask you this question, answer honestly. Just for a moment, close your eyes, think very carefully, and answer the question, do you feel the force of gravity? Okay? Who says yes? Who says no? Who is saying no because you get a question like this, you figure it's got to be a trick question, and the answer I'm looking for has got to be no? Honestly? Okay. I would say no from a certain point of view, right? And the reason I'd say no is that when I'm standing here right now, I don't actually feel being pulled down. What I feel is my feet being pushed up. My arm feels, I don't feel my arm pulled down, I feel my shoulder pulling my arm up, right? The natural tendency for me right now is to fall, and if the ground wasn't in the way, I would be sort of the natural state of what I should be doing. I should just be falling and I wouldn't feel any force, right? And in fact, if you were skydiving and the air wasn't in the way and you closed your eyes, you would not be able to tell you're falling. You wouldn't be able to feel gravity. Then you'll hit the ground and you'll feel gravity. Or the thing that is getting in the way. And so, Einstein took this idea and made it really specific. And his example was, okay, if you're in an elevator and somebody cuts the cord, while you are falling, you can't do any experiment that could distinguish whether you are falling on Earth or just floating in intergalactic space. Now, granted, eventually you hit the ground and you'll notice, but until then, everything's fine. Now, what does that mean? So here I'm sitting in my elevator and somebody's put a laser pointer on the wall and they shoot the laser beam across. If I'm floating in intergalactic space, I see this laser beam go straight across the room, right? So if I'm in free fall on Earth, I see this laser beam go straight across the room. I can't tell the difference. That's what relativity tells me. Now, watch what happens to us standing out here, standing on Earth, watching this poor soul fall in an elevator. What do you see? You see light curving, right? Guy in the elevator, since the light went straight, you standing outside since the light curved. That is what we mean by gravity curving space and time, right? What you think is a straight line, I don't think is a straight line. The straightest line I could take right now is actually falling straight from the Earth, right? That is the straight line that I want to take, and the fact that I can't take that is why I think there's a force of gravity. So the ground's keeping me off of the straight line that I want to be on. And so that is all of gravity. All now perfectly understand it, of course. No questions whatsoever. How do you make that concrete? Now, the example we're all about to do is called the rubber sheet analogy, and I just want to point out, it's an analogy. If you haven't seen XKCD before, I highly recommend it, especially for people who want to go into science. It is very, very, very nerdy, and it just points out that the rubber sheet analogy has some problems because it kind of assumes that gravity exists. So really, if you want to really understand it, you just go through the set of equations, and it's all perfectly understandable and requires a little bit more explanation. But the rubber sheet analogy is saying, like, well, you know, if you had a sheet and you kind of threw marbles around the sheet, where there were masses, you would see the marbles deflect. And what that idea is trying to get across is that the straightest possible line for a marble here is to actually curve relative to what you would think if there wasn't a mass there. It is bending space. Now, I want to point out the limitation of that analogy is that this is bending space. Right now, what the Earth is doing to me is it's bending my space and time together. It's actually bending space into time and time into space. That is not easy to picture. I can't do it. I'll be honest, I've never met anyone I think can actually do it. There are people who are very good at sort of doing tricks that make it kind of work. So. But that's the analogy. But the idea that I want to concentrate on here is something called the metric. And what the metric is the rubber sheet. It is the thing that is kind of being bent by space and time. And what it actually is how you measure distances. So think of it, you can kind of see as you get over here, each one of these grid marks is kind of 1 unit. And you see that they're getting bent. Right? They're getting extended and contracted by the fact that there are masses sitting on the rubber sheet. They're bending distances. And what that's actually doing is it's bending how you measure a meter. It is bending how you measure a second. A second here on Earth is not the same as a second 1,000,000 kilometers above the Earth. Right? They've been bent into space, and space is bent into time. And so when we talk about the expansion of the universe, the thing that is actually expanding is this measure of distance. Right? Here is another example of the slide that you saw from Professor Jha, where you can see that's not showing up. There's actually grid lines right here. And what's happening is the grid is just getting bigger. A meter stick at the beginning of the universe that was taped to the metric would get bigger over time. It would just expand. Get bigger and bigger and bigger and bigger. And that is really what is doing the expansion. That is why there's redshift, it's why the universe is getting bigger. And so it's all actually tied back into this idea of general relativity. Now, why on earth did I have that little detour? I had that detour because if mass and energy is bending the metric, what happens if you take mass and you start swinging it around, right? Then you're going to cause this rubber sheet to wobble. And if you take mass and energy and you swing it around in the right way, you can get waves in the metric. And what that means is you're getting waves in how you measure distances. So you're standing here, and if a wave came through, all of a sudden you'd get a little bit thinner. It's hard to notice, but you get a little bit thinner and actually a little bit taller, right? And then the other way, you get a little shorter and a little wider, right? If the wave came through in the right direction. I'll show you another slide in a second. And you can kind of see where I'm going with this, because here's two little kind of glowing marbles that look a little bit like the neutron star I showed you earlier, rotating around each other. And they're sending out these ripples in space-time, these waves. And they're called gravitational waves. And so how would you look for that? Well, you would look for something getting a little bit taller and a little bit thinner, or a little bit wider and a little bit shorter, over and over and over, just kind of wobbling back and forth. And it turns out you can prove that the only patterns that they can do are kind of this pattern, and then this kind of one where you go kind of in an X shape. And then you can combine these two, but these are the two possible shapes you can get for gravitational waves. But again, you want to look for one direction getting longer and another direction getting shorter. How on earth do you do that? The first thing I want to mention is that the change in the metric, the change in length that you're looking for these interesting things, is 1 part in 10 to the 22. What does that mean? It means if you have a 4 kilometer long thing that you're going to measure its length by, it will get longer or shorter by less than 1/1000th of a proton radius. Really, really small difference. Why do I say 4 kilometers? That seems very specific. Well, I say 4 kilometers because somebody built a 4-kilometer tunnel in an sort of 2 lines perpendicular to each other called LIGO. There are 2 LIGO sites, one in Louisiana, one in Washington State, and another similar experiment called Virgo that kind of is now the LIGO-Virgo collaboration. I think that one in Italy. And so you have these things, and what they're doing is sending laser beams from here. They get split. One beam gets sent down there, the same beam splits, goes over here. And you can see the overhead here. You go down, you hit a mirror, and you bounce back. And if the beam length doesn't change, then when it comes back and gets to the detector, the beams have been set up so that when one beam peaks, the other beam has a trough, and you add them up, and you don't see anything. If one length gets shorter and the other gets longer, then one beam has to travel ever so slightly further, ever so slightly further back, and you get a signal here. And so this is the LIGO detector, and it sees gravitational waves, where this entire long 4-kilometer tunnel changes by less than a proton radius. Right? And they can do this, it's incredible. I would not want to be part of the engineering team for this. Because like basically anything has this signature, right? Anything that goes wrong causes this. And in fact, the reason that they have these sites all over the world is you don't want somebody tapping on this tunnel to give you a signature that has a correlation with the signature on the other side of the earth, right? A truck downshifting on the highway in Louisiana will give you a signature, but it's unlikely you'll get the identical signature at the same time, or actually time lagged by exactly the speed of light over in Washington State. And so you can use that to sort of throw out all of your, or hopefully all of your backgrounds, right? An earthquake in this part of the world will have a different effect here than it will somewhere else. So in order to see a detectable signal of gravitational waves, to get a signal as big as 1 part in 10 to the 22, you need something pretty dramatic, like, say, smashing 2 stars together. And so the first detection by LIGO was gravitational wave in 2015, and it turned out to be 2 black holes merging, which is totally boring. I'm not going to talk about it, right? Instead, I'm going to talk about the gravitational wave found in 2017, which was 2 neutron stars merging. Why am I going to talk about this one and not this one? Well, if you throw 2 black holes together, you get gravitational waves. And it turns out you don't get light because they're black holes and they don't have stuff around them that will emit light. When you throw 2 neutron stars together, you get gravitational waves, and you've just thrown 2 neutron stars together, and you get an awful lot of light. It's actually something that we now just call a kilonova, because it's not a supernova, but it's not a nova. And it's actually the source of most of the gold in the universe, it turns out, because when you smash these 2 neutron stars together, you end up with this region that is very, very dense in neutrons, and all of a sudden the neutrons go, oh, I could much rather be a proton and an electron and fall apart. And while they're falling apart, can form all sorts of interesting heavy elements. But they'll also release a huge amount of electromagnetic radiation, which is to say light. And so this is the detection post-merger. So the gravitational wave detector saw it first. I'll come back to this in a second. And then there were follow-up observations from all over the world, finding it in various light-based telescopes. And in fact, you can ask Professor Jha about it during the question and answer, because he has a lot more to say about that being an actual observer than I do. But it was very, very exciting. But I want to just say here what this is. So this is the 2 LIGO detectors and the Virgo detector. And they're showing time, frequency, so the rate of these gravitational wave wiggles, right? And the more yellow it is, the brighter the peak. The bigger the amplitude, the more the tunnel is changing length. And so Virgo didn't see anything. LIGO at Hanford and Livingston, you can see this line, and is sweeping up in frequency, because these things are spinning in, they're spinning in, they're spinning in, and then all of a sudden they crash together. So they're going faster and faster and faster and faster right before the crash. So that's why it's going up. It turns out that this is in optical in the auditory range. So you can actually play the chirp. You can hear the sound of two neutron stars crashing. You don't have to like upsample it or anything like that. And it's getting louder towards the end. And so given the signal that these saw and the fact that Virgo didn't see anything, they could actually determine where on the sky this thing needed to be. And then they could go tell the astronomers, and I think how many galaxies did they have to check? It was like a list of 30 or something like that. They said it's in this tiny region of the sky, there are 30 galaxies there-ish, go check all of them, right? And it was pretty early on the list. They found this one. And this is really cool. This is a gravitational wave signature. This is in time, so seconds and then days, gravitational waves. And we saw it in gamma rays, we saw it in X-rays, we saw it in UV, we saw it in optical, we saw it in IR, we saw it in radio. So this is the beginning of what we call multi-messenger astronomy, because you're seeing it in not just photons, but also in gravitational waves. But very, very cool. There's an immense amount of physics that we can learn from this. But what on earth does this have to do with the rest of this evening? Why am I bringing this up, right? Well, what does LIGO measure? It measures a gravitational wave frequency. Basically, the frequency of the gravitational waves tells you how fast these stars are spinning around each other. That's set by the rate at which these are spinning, which is set by the mass of the neutron stars and their redshift. It's just actually Kepler's laws. If you understand how planets orbit the sun, it's very, very similar with minor corrections from Einstein. You also get an amplitude, how much the metric is changing. And that's set by the mass of the stars and their redshift. But this is sort of the amplitude of the wave. And as you get further and further and further from the source, the wave gets smaller and smaller and smaller. As you drop that stone in the water and the waves go smaller and smaller over as you get further away. So it's set by the distance, right? And so you have the mass, you have the redshift, mass, redshift, and distance. Those are the two things you can measure. If somebody could give you the redshift, then you could use one of those measurements to get the mass, and then you can use the amplitude. So the frequency would give you the mass, and then the amplitude would give you the distance. But you need the redshift. And if it was just black holes colliding, that wouldn't help, because there's no optical signature. But the fact that it's neutron stars means we can look for the kilonova, find the galaxy that it existed in, find the redshift from that galaxy, then use the frequency, sort of listen, so this is why it's called a standard siren, listen to the frequency, and then use the amplitude to get the distance. And so, we know the name of the galaxy, we can measure its redshift, and you can then get a distance and a redshift. Now you can put this thing on a Hubble diagram, and you can figure out what the Hubble constant must have been for this object. And it's a distance measure that is completely separate from supernova. In fact, it's completely separate from all of the rungs of the distance ladder. You don't need it to actually know the distance to the Cepheids. You don't need to know the distance to Mars or to the nearest star or anything. You just need to do this measurement. You have a completely distinct distance ladder. And I'll show another plot actually of this in a second. Okay, so here is the Planck. So this is H0, the thing that we're talking about tonight. Here is the Planck measurement. Not the most recent one, unfortunately, but it didn't shift very much. And here's the Shoes measurement. You can see they don't line up. We have exactly one of these signatures, and there are some uncertainties about any given neutron star merger that can change what the answer is. And so what this is showing you is basically the probability of H0 being a particular value based on those uncertainties. And so you see it peaks right here, which is annoyingly right in between the two answers. But also look at the width of this, right? Yeah, this is the most probable answer, but it's very wide. So this single measurement is never going to resolve which of these two things is the right answer, right? But that's okay, because we just turned on LIGO and Virgo, and we saw something almost immediately. So if you keep waiting, what this is showing is, okay, just collect up, I think there's like 50 neutron star mergers here, and each of them will be uncertain. But if you keep adding up, it's a statistical uncertainty, it's not a systematic uncertainty. So you just keep adding them all up and see, well, which value is most likely? This one, this one, and this one, this one, keep adding them up, and eventually you'll be able to recover, say, this black line. Right? So this is just a simulation, it's not really data. Just saying this is what you would get if you had all of these neutron star mergers. And then there was this paper recently that thankfully did this plot for me, so I don't need to guess. This is the number of neutron star mergers expected as a function of time, so 2019 to 2026. By 2026, we expect a couple hundred of these, 200. This is the error on this measurement of H0 that we expect. So by 2026, we expect to get down to 1%. 1% is more or less the Planck error. 3% is the Schu's error. So within a decade, this measurement should be comparable to the smaller error bar in this plot. And that should be sufficient to distinguish between this value and this value. And if it sits right in the middle, that's going to be super annoying. But it's really cool because it's a completely separate measurement. It's a completely separate measurement, and it has the potential to do a measurement of H0 that will hopefully resolve this tension or just make the situation even more confusing. But the other nice thing is that it will be done in a relatively short time scale, at least by the scale of building these giant experiments and doing these sorts of things. So with that, I'm going to conclude, and while that's going on, I just found this simulation of a black hole merger. It's not a neutron star merger, but it's pretty cool, so I'll let that play. This is the two black holes. This is the gravitational wave signature. As this oscillates, the two lengths of the LIGO tunnels are getting longer and shorter. So just kind of, it's counting down. No, there's no sound. It's just, okay. So with that, I'm done.
Before we go to the panel discussion?
So regarding the gravitational waves being a method of like using a standard candle for very far distances, how reliable would this method be if we have to also account for, let's say, certain things being away between the neutron star orbiting each other and us? If the ripples are passing through other things.
So the wonderful thing about gravity is that it's a tremendously weak force. You may say, how on earth is gravity a tremendously weak force? Let me say it this way. The entire Earth versus me, I win. All right? Electromagnetism is tremendously strong compared to gravity. And what that means is a gravitational wave passing through basically anything. There is no index of refraction for gravitational waves passing through matter. Or there is, but it's basically not negligible. So almost nothing can stop that wave going through. That does mean when it gets here, it's almost impossible to see, right? So you win some, you lose some, but we figured out how to at least measure these kinds of signatures. And so that's one of the advantages to this. So the question there.
Yeah, going back to the previous speaker as well, with the Hubble constant being a time-dependent.
Yes.
Wouldn't that then matter where the source of
Yes.
it is? Because obviously they're going to be different times. How are you sure you're not measuring the Hubble constant from a different time when the Hubble constant was a different value?
So we've been sort of cheating and not really getting too much into that. The distances that I'm talking about here, like the neutron star merger, we know is about 40 megaparsecs away. And the supernova are something on that length scale. So actually, the direct comparison of standard sirens would be to the supernova measurement. And we know that actually from the distance measurement that we get from this. It's how we nail down where this thing should be. And 40 million parsecs is tremendously far, but in the history of the universe, it's basically today. So it's not that big of a change. H should not have evolved that much. The evolution from the early universe, from the CMB to today, I mean, that is, a lot can happen. A lot did happen between those that and today. We believe we understand it, and my sort of day job, when I'm not talking about gravitational waves, is actually looking for new physics. And I'm interested in dark matter and all sorts of ways of new physics. The thing we would love is if we knew for sure that Planck and supernova were giving different answers for H0, because what that would mean is that the evolution from the Planck measurement to today was wrong. And that means that there's something new between then and today that has changed how I look. I'm just extrapolating, saying, oh, you know, given that measurement, that means today the value should be this. And if they're not the same, then I did something wrong. And that's great, because it means we get to figure out what it was.
When you say that LIGO picked up a source of a gravitational wave from two neutron stars colliding, and then you told the astronomers to go look in.
Well, I did. I'm not affiliated.
Oh, not you personally. Does that mean that gravitational waves travel faster than?
No, I mean, if we had been lucky enough that somebody had been pointing a telescope directly at the thing when it went off, we would have, first we would have had more science, because we would have seen the actual like turn on. You know, telescopes don't look everywhere. Maybe we can have sort of tell a little bit more about the story, but I mean, there's a network of observatories around the world. Like when things happen, people's phones ring. If the supernova goes off in the galaxy, people's phones will ring, and then they will run to their computer and start redirecting telescopes to look in the likely location. So my understanding of what happened is that this happened. The LIGO people got on the phone and said, we believe something has happened. Our best guess is it's here. The moment you can, please point your telescope there. And in fact, people, like these things are embargoed. Like they don't tell the world about it until they have the chance to do the math correctly. People have guessed how many gravitational wave events have been seen based on how many times telescopes around the world stopped doing what they were supposed to be doing and started looking in random places in the sky. And they're right. They get the right answer. So sort of forensic snooping. I think we should probably start there.
Yeah, okay, why don't we, let's adjourn to the panel discussion and you continue to ask your questions. So if you guys want to come up and sit at the panel table.
I'll take this off so I don't have an advantage.